Hello, can you hear me? Hello.
Yes, sir. Good evening, sir. We can hear you.
Yeah, okay. Okay. So yesterday we have discussed about the dialectics. Okay, the dialectics basics have started, and it's also definitions and types of dialectics. I have discussed the dialectics. Let's continue with what we are doing. Okay. So first of all, the orientational electronic polarization. Okay, the electronic polarization I have started and we have progressed a bit. The derivation as well. Very quickly, I'll tell you what the dialectic because the members today are different from yesterday. Okay, anyway. Hmm. So here the dialectics are depends where usually called insulating materials and not just insulating materials, but they are a bit different from the insulating materials. That's why they're called dielectric materials. How I'll tell you. See here, the conduction doesn't take place in the dielectric substances. Okay, the more we try to conduct the electricity, the more it it goes away from the conduction. So in the sense, actually, the goes away from the conduction in the sense that we have positive charges and negative charges inside the substance, and when we are trying to send the electricity to it, then the positive charges and negative charges get separated. Okay. Then the distance between the positive charge and the negative charge, usually we call it as a dipole, and like that there are so many sets of dipoles from. Okay, the positive charge in the sense nucleus. Okay, and the in that atom we have here one nucleus with the electrons being separated by some distance. Okay, when the electrification has been given, then as a result the charges gets separated. Okay, this is one dipole and another dipole. Like that, there are so many sets of dipoles being produced. And the process of production of dipoles is called polarization. Okay, and apart from that, we have also discussed about the electronic polarization. The electronic polarization is the one where the substance, the dielectric substance has been given the electric field. Then as a result, the electric charges, they're all like they all come at one place. Okay, and they will never overlap. Okay, so if you say they all come at one place, it doesn't mean that they overlap. Okay, they all come at one place, and the positive charges all come at one place and being separated by some distance, and it creates the electrons all in one place, creates some kind of cloud. Okay, and this cloud will just gets shifted when the electric field has been applied. Okay, and that shift is proportional to the electric field. Okay, so that's what we have discussed yesterday, and we have done the derivation as well, and already discussed about the dielectric constant, the electric polarization, polarizability. Okay, and talked about the electronic polarization derivation as well. So how we can discuss about the electronic polarization is just now I told you about that the cloud has been formed, the electric cloud has been formed, and that is proportional to the field and the field. Okay, and there are two kinds of forces being acting here. One is Lorentz force, other one is Coulombic force. Lorentz force is one which goes away from the charges. I mean, when the electric field has been applied, the positive and negative charges will get separated. Okay, and that force is called Lorentz force. And there is another kind of force which also acts here, that is Coulombic force. Coulombic force always tries to bring the um, charges together. Okay, that's Coulombic force, they're equal and opposite. And we have done the derivation as well to, to derive it. Okay, that's fine. And then fine, further we will just move on to the ionic polarization is also some kind of a derivations here. Ionic polarization. Okay. Ion polarization usually refers to the displacement of cations and anions. Okay, here positive and negative. Instead of talking about the positive and negative charges, we talk about the cations and anions. Okay, once again, due to the displacement of cations and anions, okay, the ionic polarization will take place. Okay, then here see, let us say that the displacements towards the right side we call it as x1. Okay, we call them as x1, and the ions, okay, negative ions move towards the left by x2, x1, x2. Okay, we are writing. Okay, for instance, then assuming that each unit cell has one cation and one anion, the resultant dipole moment is given by. I'll show you the equation. The resultant dipole moment. Okay, dipole moment is given by this per unit cell. Okay, per one unit cell, is given by mu is equals to E times x1 plus x2. Mu is equals to x1 plus x2. Okay, so this was the equation. Okay, first of all, initially, see, ionic polarization is given. We are talking about anions and cations. Okay, the displacement of cations and anions in opposite direction and occur in an usually happens in ionic solid. Okay, suppose if you consider the positive ions move towards the right by x1 and the negative ions move towards the left by x2, then what happens is, assuming that each unit has one cation and one anion, the resultant dipole moment per unit cell due to the ionic displacement is given by that equation. Okay, mu is equals to E times of x1 plus x2. Okay, see, when there is a displacement here on the left hand side and right hand side as well, there will be always some kind of restoring forces to bring them back. Okay, for instance, how you understand the restoring force? I'll tell you. I have pendulum, for instance. Okay, we have pendulum. It's been connected, then being pulled, for instance. Okay, then what happens? It goes to the extreme and come back. Okay, it goes and come back. And here, if it goes, then there will be some kind of restoring force to bring it back. So how the restoring forces are acting? So also here, the restoring forces will be acting, and that we name it as beta 1 and beta 2. Okay, we name here beta 1 and beta 2. Those are said to be the restoring force constants. Restoring force constants of cation and anion, and F is said to be the force. Okay, so F is beta 1 x1 equals beta 2 x2. Okay, so yes, if beta 1, if beta 1 and beta 2, if beta 1 and beta 2 are said to be the restoring force constants of cation and anion, and F newtons is the force due to the applied field. Okay, that's the force due to applied. I'll show you what's force due to applied field. Applied field. Because of this applied field, then F is given by beta 1 x1 is equals to beta 2 x2. Okay. Once again, if beta 1, beta 2 are said to be the restoring force constants of cation and anion, and F newtons is the force due to applied field, F is equals to beta 1 x1 is equals to beta 2 x2. Okay, and further we write x1. So just we write here x1 is equals to F by beta 1. Then actually the restoring force constant depends upon the mass of the ion and angular frequency of the molecule. So further we write here x1 is equals to small e by m omega naught square. Okay, restoring force constant depends upon the mass of the ion, and the angular frequency of the molecule. Okay, so we write here the restoring force constants depends upon the mass of the ion and angular frequency of the molecule. in which the answer present. So we write here x1 is equals to small e times capital E by m naught omega naught square. Okay, that's the angular frequency. Okay, and x2 we write here small e times capital E by capital M omega naught square. Okay, that's the mass of the ion. Okay, so further x3 is equals to small e times capital E by capital M omega naught square. Okay, and where M is said to be the mass of the negative. M is said to be the mass of the negative mass of the negative ion. Mass of the negative ion. Okay, and further x1 plus x2. x1 plus x2 is given by small e times capital E by omega naught square. And we take this common, we put together and take a common to write like this. x1 plus x2. x1 plus x2 is given by this. x1 plus x2 is equals to small e times capital E by omega naught square multiplied by 1 by m. 1 by m plus 1 by small.
Sir, what are X1 and X2, sir, here? Sorry, I missed that. There is distortion. I couldn't hear properly.
x1, x2, there are displacements. Okay, so we are talking about anions, cations. Okay. Anions and cations we are talking about. And the anions, cations, they make displacements. Okay, they make displacements towards the right side and the left side. And exponentials are said to be the displacement. How much they got displaced. Okay, that is what x1 and x2 respectively, right?
Okay, the displacements. Okay, thank you.
Yeah, displacements. Okay, fine. Further, let's continue with x1 plus x2, and further we write here.
Sir, actually, your voice is distorted, sir. I'm not able to hear properly. If it isn't just for me or for others, I'm not sure.
You're not able to hear.
I can hear, but there is a lot of static in between. So that's the only.
So what's the problem here? See, it shows correct. Everything is correct here. I don't know. If there is some problem with the network you are using a mobile, or I don't know. If that pick, if it is not picking the signal properly, I don't know.
Okay.
But here, from my side, it's all okay.
Okay, sir. Sorry about that. Yeah, please continue.
No problem. Okay, so mu equals E times x1 plus x2, x1 plus x2, and it's just given by small E squares E by omega naught square, and 1 by m plus of 1 by small m. Okay, so further I see this one. Mu equals to small e multiplied by x1 plus x2 is equals to e square capital E by omega naught square 1 by m plus 1 by small m. Okay, that's the mu. And further, alpha I, that's the inequality. But a very simple derivation. Small alpha I is equals to mu by E. Okay, therefore, E square by omega naught square times 1 by m plus 1 by small m. That's what the final form of the equation. Once again, I'll show you. Mu I is equals to alpha I is equals to mu by E, which is equals to E square by omega naught square 1 by m plus 1 by small m. Okay, so this what see the generally in the exams what they will be asking is that discuss about the various types of polarizations, namely the electronic polarization, ionic polarization, and the orientation polarization. So all you have to do is to describe about the electronic polarization first. Okay, a little bit of derivation, 3 to 4 steps, and then here we have the ionic polarization, and further the orientation polarization. Okay, so let's go to the orientation polarization. Okay, orientational polarization is something when we talk about some chemical compound. Okay, see, usually this dielectric substances, as I have mentioned in the previous class, that these dielectric substances are not restricted to solids. Okay, they are not restricted to solids. They can be, these dielectric substances can be available in liquids, they can be in gases, maybe in solids. Okay, okay. So in various forms you can be found. So first of all, to begin with here in the methane molecule, the methane molecule is CH4 actually. See here. The methane molecule, the methane molecule is CH4. We are talking about orientational polarization. Okay, in the methane molecule CH4, the center of negative and positive charges coincide. Here, see, we have to first of all understand that the whenever we are talking about the dielectrics, we are all talking about the positive charges and the negative charges. And the more we are trying to send the electricity, the more it opposes. But the more it opposes in the sense that the positive charges and negative charges, they go away from each other. Because they are going away from each other, the conductivity does not take place. That's the one thing. So every time the concept remains same, like positive charges, negative charges. In the previous case, we have taken anions, cations, and here in this case, we are taking the positive charges and negative charges. Okay. So here, what happens is usually in the methane, the positive charges and the negative charges they coincide. This is why I am talking about this. I'll tell you. See, there is no point in talking about the coinciding. We are not talking about the coincidence, but still there is a link. I'll tell you. Do not get confused. Okay, here's the methane molecule in CH4. CH4, the positive and negative charges coincide. Okay, when they coincide, there is no dipole. Here, see, when they coincide, what happens here? No dipole. No dipole. No dipole. Okay, when they coincide, no. Only when they go away from each other, the dipole moment forms. Okay. So, but here chloromethane, CH3Cl, CH3Cl, that is chloromethane, 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 that is, okay, CH3Cl. In chloromethane, the positive and negative charges do not coincide, okay. Once again, in CH3Cl, the positive and negative charges do not coincide. The reason is that the electronegativity of chlorine is more than that of the hydrogen. The chlorine atoms pulls the bonding electrons to itself more strongly than hydrogen. Okay, so that's why the positive and negative charges do not coincide. Once again, if you have missed, see, in CH3Cl, that is chloromethane, the positive and negative charges do not coincide. Since the electronegativity of chlorine is more than that of the hydrogen, the chlorine atom pulls the bonding electrons to itself more strongly than hydrogen. Okay, so that's the reason. And even in the absence of electric field, the molecule carries a dipole moment. So you don't have to apply the electric field, even if you are not applying the electric field, that they will just get separated. Then you can understand that CH3Cl, the chloromethane, is said to be the dielectric gas. Okay, so that's the thing. Okay, and then when the electric field has been applied, then the molecules which possess permanent dipole moment, they will be aligning in the direction of the applied field. Okay, so when the field has been applied, then they will be aligning in the applied direction field, and then the polarization due to such element. So here polarization is said to be taken. Okay, so see, I'll tell you. I'll draw the diagram and show this is the positive charge and this is a negative charge. This is called the okay. This is what the dipole. Okay, the positive charge and the negative charge being separated by some distance, and that's what we call it as dipole. Okay, and like that, there are some sets of dipoles. I'll quickly draw it and show it to you. That some sets of dipoles like this. In a substance, the positive charge, negative charges, like that. Okay, there are some sets of dipoles which are being formed, and that is actually preventing the conduction. Okay, so one set of dipole, another set of dipole, like this. There are so many sets of dipoles being formed. Then that is actually the polarization. Okay, and here in this case, the polarization due to such alignment is called orientational polarization. Okay, that is what the orientation polarization has been defined. So here P naught, we call it as P naught. Previously we have taken Pi, and here we are taking P naught. Okay, that is orientation polarization N mu. Okay, polarization P naught is equal to N mu, and further N mu square E by 3 kT. It is defined like that. And further we write N alpha naught E. Okay, and this part I'll show you, that is taken as alpha P naught. Okay, is equals to N alpha naught E, and alpha naught is given by P by N E. P naught by N is equals to mu square by 3. Okay, so once again, okay, P naught is equals to N mu. Okay, and further we write here N mu square E by 3 kT, and mu square E by 3 kT, mu square E by 3 kT has been written, and from there we write here mu square by 3 kT has been taken as alpha naught. Okay, that is orientational polarizability. Alpha naught is equals to P naught by Ne, and which is equals to mu square by 3 kT. Okay, this is what is said to be the mu square by 3 kT. Right, fine. Further, and the orientational polarization is inversely proportional to the absolute temperature. That's one point. But, okay, so with this, the orientational polarization has been done. And now we have a very important thing to be discussed. That is to be the internal field. Okay, the internal field of the dielectrics we will discuss, and we have the Clausius-Moissault relation. As per the syllabus, we have here Clausius-Moissault relation as well. Okay. Yeah. Internal field, this is very important question for the examination. Okay, we have to derive this by all means and understand. Okay, see, this needs lots of imagination. How the dielectric substance in which the internal field has to be understood. Okay, so how I'll tell you. First of all, to begin with, the internal field or sometimes the local field, how the questions will be asked in the examination. You have to be a bit careful in while writing. In the examination, they will be asking that discuss the internal field of dielectric substance. Okay, they will be asking straight away like that. Or sometimes they will be asking, discuss the local field. Okay, local field in case of a dielectric, they will be asking like this. Okay, the internal field or local field is one and the same. Okay, for this purpose, let's discuss. We have a lengthy derivation, of course. Okay, but still I try to explain. We have here actually the internal field. The internal field, how we have to understand is that suppose we have some substances. We have a substance and the electric field has been applied to that dielectric substance. Then what type of forces are acting in a particular place we are talking about? Okay, once again, we have a dielectric substance. The electric field has been applied to that particular substance. That is actually induced electric field. Induced means we are not actually directly contacting, but we are keeping a field, electric field, and putting a dielectric substance in between like that. Okay, it's not touching. Then the electric field will act on the dielectric substance, and that field will be acting over a particular place. How much of the field which is acting over a particular place, a particular volume, and what are the different types of fields which are acting over a particular space we are talking about. This is that's what I'm telling you. You have to have loads of imagination, and that particular field, uh, specimen, in that we have taken a small area, in that a sphere has been taken, in that a cavity, round of a type of a cavity has been taken, the internal field inside, okay, and how about because of surface and because of the uh, inside, okay, like this, there are so many kinds of forces being acting. First, to begin with here, the internal field is defined as, okay, A. Internal field is A, which is given by E1 plus E2, E1 plus E2 plus E3 plus E4. So you can understand that there are four types of forces here. Okay, four types of forces, not forces. Okay, some E A is the internal field which is given by E1. Okay, some E1 is the field intensity. I'll tell you what is what. Okay, E1 is said to be the field intensity. E1 is said to be the field intensity. E1 is said to be the field intensity due to charge density on plates. Okay, E1 is said to be the field intensity, field intensity, field intensity due to charge density on plates. Okay, I'll tell you what is what. Quickly see. So capital A, okay, that's the internal field, is given by E1 plus E2 plus E3 plus E4. Okay, there is a system in learning. I'll tell you step by step. Okay, so where E1 is said to be the in field intensity, E1 is said to be the field intensity due to charge density on plates. E1 is the field intensity due to charge density on plates, because the charge density is existing on the plates. Okay, and E1 needs to be considered. Okay, there are four kinds of forces. Okay, field, that is intensity. Next, E2 is the charge density induced on two sides of a dielectric. E2 is the charge density induced on two sides of dielectric. First one is field density, field intensity. Okay, and the second one is charge density due to induced on the two sides of a dielectric. Okay, and E3 is the field intensity due to other atoms in cavity. I told you cavity, cavity is a kind of a hole. Okay, so imagine that we have a dielectric substance. In that particular substance, there are some cavities there, and then in that cavity, field intensity has been present there. Okay, that is E3, and E4 is the field intensity due to polarization charges on the surface of the cavity, because of the surface of the cavity. Okay, imagine, I'll draw the diagram. Yeah, I just wanted to show you what I'm talking about. Okay, that's the dielectric substance, for instance. Okay, and it's been put some field. Okay, the positive charges and the negative charges. Okay, I'll just show you what I'm talking about. Then you'll understand much better. See, that's the induced field on the left side and the right hand side. Okay, and we should not touch anything. and there is a dielectric substance in between, and one particular place where we are talking about kind of cavity is a hole present, and there are four types of fields which will be acting over there. See how imaginative you have to start imagining. There are so many things to be imagined here. Okay, so there are field intensities due to charge density on plate. First point, that is E1, and next point is the charge density induced two sides of a dielectric. That's another force, and due to the cavity, cavity, and due to the surface on the cavity. So there are E1, E2 plus E3, and E. There are four fields which are acting on for there. Okay, I'll draw the diagram. Okay, I'll show. Then you will be understanding things better. I'll show you. That's what the diagram is. Okay. See the positive charges and the negative charges. Okay. And those are said to be the induced field onto the dielectric substance. That dielectric substance, rectangular one, is the dielectric substance. Okay. Yeah, that's the dielectric substance. Okay, the positive and negative charges, that's induced field. It's been connected to a power supply serial. Okay, that means the induced field is acting on the dielectric substance, and there is a cavity of the circle. Okay, inside inside that there is a circle. Okay, circle up there. Yeah, circle, and that's the surface area we are talking about. In that surface area, we are talking about a small cavity, and because of that cavity, there will be some kind of field which will be acting, okay, inside, and we are talking about surface. Okay, so that's how we have to talk about. Now, if you zoom this picture, okay, if you zoom this picture, and this will come down. See, that's the next one. If you zoom, then that's what is going to come here today. Okay, so I'll tell you what is that. Okay, this actually is the zoom part, the positive charges and the negative charges. Okay, and we are talking about some, let us say, that we in the text we are giving us, see, the same diagram of the action. And I'll show you, but you must know that what are these. Okay, so okay. See, this is what the diagram. Okay, if that's a zoom out of the previous discussion, what we have done, just now I told you that the electric field has been induced onto the dielectric sections, the positive charges and the negative charges distribution will be there, and then we are talking about a small cavity, and here there's an angle theta. See here, usually in the textbooks they don't mention what is this angle theta. That's angle there. Okay, see how to understand that. Then radiation is like we are talking about the plates, two plates. We have here the positive plate and the negative plate. Okay, this is connected to the electric field. Okay, electricity has been passed. When the electricity has been passed, then here some kind of the electric field will be falling onto the dielectric substance. When the electric field falls over the plate, then it falls with some kind of angle. That angle is okay. So you have to understand that the field intensity, okay, can be felt on the dielectric substance, and that goes with some angle. That's the angle theta. Usually they don't mention in the textbooks. So that you have to understand very carefully here. Okay, and further we move on to how we will derive this value. Okay, so further what we see is E1. Okay, so what is this derivation here? We will try to understand E1 plus E2 plus E3 plus E4, and the total is said to be the incomplete. Okay, so step by step we will try to work this out. What is it? Okay, from the field theory, E1 is given by D by epsilon naught. Okay, capital D P plus epsilon naught E. Okay, and you have attended classes before. I told you about the electric displacement. Okay, those are the relations. Okay, I'll show you. E1 is given by D by epsilon naught, and capital D is given by P plus epsilon naught E. Okay, those are the relations. Okay, and further we write here E1. E1 is equals to P plus epsilon naught E. P plus epsilon E by epsilon naught, which is equals to E plus P by epsilon naught. We name this equation. Once again, we write here. I'll show you the equations. Okay, E1 is equals to D by epsilon naught. E1 is D by epsilon naught, and D is equals to P by epsilon E. E1 is equals to D plus epsilon E by epsilon naught. Okay, and E is equals to P by epsilon, just rearranging like that. Okay, and we name it as equation 1, and that's about E1 we have got. And further, E2 is the phase into the electron. Okay, induced sides of the two sides of the dialectic, and E is given by minus of P by epsilon naught. Okay, minus of P by epsilon naught. E2 is minus of P by epsilon naught. Okay, and E3 is said to be 0. Okay, E3 is 0 because of symmetry. Actually, E3 will become 0 because the field intensity dA due to other atoms contained in the cavity, and for a cubic structure. Okay, and for a cubic structure, the E3 is taken as 0. Okay, you name it as equation 3. And now we have to calculate E4. E4 is a bit lengthy. Okay, where you will be calculating. Okay, and then we'll be adding up to get the interval. How I tell you. So we write here to calculate E4. We write here dA is equals to 2 pi times. We use some kind of trigonometry. PQ times QR. PQ times QR. dA equals to 2 pi times dA is equals to 2 pi times PQ times QR. Okay, and sine theta is PQ by R, and PQ is equals to R sine theta, and d theta is QR by R, and further QR is equals to R d theta. Okay, see further solution. Okay, see, as I have shown picture, this one I'll show it again. That's the picture. Okay, so here see we are writing angular theta, we have P, we have Q, we have R. Okay, the little bit of geometry, little bit of trigonometry has been used and been written like that. dA is equals to 2 pi times PQ times QR, and the sine theta is given by PQ by R, and PQ is equals to R sine theta. And first step, when you write, the other steps follows. Okay, that's easy. And d theta is given by QR by R, and QR is given by R d theta. Okay, just cross multiply. Okay, and further you have got some equations now. And now next step is to substitute. Okay, substitute these values, and I'll tell you what you have to do is, this is quite easy actually. Okay, I don't know how they have mentioned in your booklet. Okay, R sine theta times R d theta. R d theta is equals to 2 pi R square sine theta times d theta. Okay, so if you substitute, this is what you are going to get. dA is equals to 2 pi times R sine theta multiplied by R d theta, which is equals to 2 pi R square sine theta d theta. Okay, and now it's been linked with the next step. How I'll tell you. Charge on density, charge on surface, dA. dA is given by P is equals to P cos theta dA. So the dA already we have got it, and that's what we are going to substitute here. Okay, dQ is equals to P cos theta dA. Okay, once again, dA is given by 2 pi times R sine theta multiplied by R d theta is equals to 2 pi R square sine theta d theta. dA is equals to 2 pi times R sine theta times R d theta is equals to 2 pi R square sine theta d theta. Okay, and the charge on the surface dA is done by dQ is equals to P cos theta dA. dQ is equals to P cos theta dA. Okay, and further what you have to do, you substitute the value of dA in the last equation, then okay, some changes, all that I'll show you. So what you have to do is to substitute the value of dA, dQ is equals to P cos theta times 2 pi R square. There are few steps you have to remember, and the rest of them are simplifications, substitutions. They are easy. Okay. P times 2 pi R square sine theta cos theta d theta. Okay. So dQ is equals to P cos theta 2 pi R square sine theta d theta is equals to P times 2 pi R square sine theta cos theta d theta. Okay. So further, then the direction theta, when theta equals 0, what happens here? dE4 is given by dQ cos theta by 4 pi epsilon naught R square, which is equals to P times 2 pi R square sine theta cos theta d theta times cos theta. Okay. Further, dE4. Okay. dE4 is given by dQ cos theta by 4 pi epsilon naught R square, which is equals to P times 2 pi R square sine theta cos theta d theta times cos theta. Further, we write here dE4 equals to P sine theta cos square theta d theta by 2 epsilon naught. Further, we integrate this. Okay, dE4 is equals to P by 2 epsilon naught integration of 0 to pi sine theta cos square theta d theta is done by P by 2 epsilon naught integration of 0 to pi cos square theta times dl minus cos theta. Okay, so we do the integration of dE4 is 1 by p by 2 epsilon naught, integration of 0 to pi, sin theta, cos square theta, d theta is 1 by p by 2 epsilon naught, integration of 0 to pi, cos square theta, d times of minus cos theta. Further, we simplify it and we assume cos theta as x. Here we assume cos theta as x. Then integration of dE4 is given by minus p by 2 epsilon naught, integration of 0 to pi. In order to simplify, we assume this as x, and E4 is given by p by 2 epsilon naught and x cube by 3. Yes, we are doing integration. Further, minus p by 2 epsilon naught cos cube theta by 3, 0 to pi, and further simplification gives you p by 3 epsilon naught. Finally, you will be getting that as this p by 3 epsilon naught. So E4 is 1 by p by 3 epsilon naught. Okay, so we will work on here now E4. So that's what equation. And all I have to do is to add up all E local field is given by E1 local field, E1 plus E2 plus E3 plus E4. Okay, is given by E plus P by epsilon naught minus P by epsilon naught plus 0 plus P by 3 epsilon naught. So further simplifications, what you will be getting is E plus P by 3 epsilon naught. Okay, so after substituting E1, E2, E3 and E4, okay, and that's the one which is in the rectangular box. E plus P by 3 epsilon naught. Okay, that's it. This is what is to be the internal field. Because see, there is an every reason I'll tell you. You must remember this final form of this equation, because the final form of this equation will be taken as first equation of the next derivation. Next derivation is Clausius-Mosotty relation. Sometimes Clausius-Mosotty relation may be given for an answer type question, okay, or a short type question also they will be. I don't know. Sometimes they will be giving, some professors they will be giving as a short question also. Okay, this is all mathematics, completely mathematics. Okay, this Clausius-Mosotty relation. I'll write down Clausius-Mosotty relation. That's the relation. Okay. Clausius-Mosotty relation. Okay. This to understand this Clausius-Mosotty relation, they're not that much easy. See here, first time when you're listening to, they are bit typical, but see, they're not impossible. Okay, they're not impossible to understand or something like that. No, nothing. That's what I'm saying. There is a step-by-step procedure that you have to follow. You have to understand the basics, then you will understand this. Okay, so the Clausius-Mosotty relation is talking about a dielectric substance in which a Clausius-Mosotty name also like this. Okay, they have formulated a derivation about what a cubic structure. Actually, here They have taken a cubic structure. What they have taken is, let's consider a elemental dielectric having a cubic structure. Okay, cubic structure has been taken. There are no ions. Here there are no ions and permanent dipoles in these materials, and no permanent dipoles. Okay, no ions and no permanent dipoles here. Okay, that's the assumption. Then what happens? The ionic polarizability, the orientation polarizability, they all become zero. Okay, ionic polarization and orientation polarization will become zero. First of all, assume, this is what assumption. Okay, like a cubic structure has been taken. Okay, in a dielectric substance, the cubic structure has been taken, and here the ionic polarization, the orientation polarization has been taken as zero. That's the first assumption. Okay, so here that's what I'll write down here. Alpha I equals to alpha naught equals to zero. This is the basic assumption. That's the first assumption. Alpha I is equals to alpha naught is equals to zero. Okay, that's the assumption. Further, we write here the equations, just 3 or 4 steps actually here, but little bit of the we have to consider the left hand side, moving on to the left hand side, onto the right hand side, simplifying is the rest of the derivation. Okay, so not that difficult to do, but we will start with the polarization. P is given by n alpha EI. See this what EI is. See, first of all, the polarization P is given by n times alpha E times EI. EI is the internal field, please. Okay, EI is said to be the internal field. Okay, so here C, which is given by n alpha E times E plus the output of the previous equation I'm writing here. Okay, n alpha E is given by n alpha E is given by n alpha E multiplied by E plus P by 3 epsilon naught. Okay, the previous form, that is EI. Okay, that is being written. Then what will happen is, this is equals to P, and now we have to just send to the other side. Okay, take P as common. Okay, 1 minus n alpha E by 3 epsilon naught being written is equals to n alpha E times capital E. Okay, and P is given by, we have to separate P. Okay, from this equation, you have to separate P. Okay, send it to the right hand side. Okay, that's what I'm going to write here. Then you will be getting here P is equals to n alpha E times E by 1 minus n alpha E by 3 epsilon naught. Okay, name it as number 1 equation. Okay, so that's what we will be getting. P is equals to n alpha E by 1 minus n alpha E by 3 epsilon, just sending to the right hand side, and we write here the displacement. Displacement equation is given by D is equals to P plus epsilon E. Displacement D is given by P plus epsilon E. Okay, and also we have here D. We can write P from this above equation. P is equals to D minus epsilon. Okay, so this just a shuffling, send it to the other side, find out what is P. P is equals to D minus epsilon E. Okay, P is equals to D minus epsilon E. Now what you have to do, divide both sides by E. Divide both sides by E. Okay, that's what you have to do it. Okay, just divide both sides by E and simplify it. Then you will be getting P equals E multiplied by epsilon naught epsilon R minus 1. That's the equation number 2. Okay, that's the equation number 2. P is equals to E epsilon naught epsilon R minus 1. Okay. And now what we have, we have got P equation from the equation 1 and P from the equation number 2. Now all we have to do is to equate it. Equate the first and second equations. Okay, we have to equate 1 equals to, we have to equate this first and second equations. Okay, once we do the first and second equations and simplify, shuffle to get the n alpha e by 3 epsilon naught, we'll be getting. How I'll tell you. You have to derive it a bit here, how I think. So n alpha e times e by 1 minus n alpha e by 3 epsilon naught equals e epsilon naught into epsilon r minus 1. Okay, so write down this left hand side and right hand side like this. Okay, left side and right side. Okay, both sides you have to write. Okay, this side, that side, and start cancelling if any. Okay, on the other sides, multiply it, divide it, take LCM, send it to the other side. These things are not that much easy. Okay, so they're not that much difficult, but all you have to do is to multiply this. Okay, taking LCM, simplify it, and finally, what you must get is absolutely you'll be getting after simplifying it anyway. You'll be getting here epsilon r plus 2 divided by epsilon r minus 1 is equals to n alpha e n alpha e by 3 epsilon. N is actually the number of molecules. Okay, so this is what you will be getting here. Epsilon r plus 2 multiply divided by epsilon r minus 1 equals to n alpha e by 3 epsilon naught. This is Clausius-Moisseiff relation. Okay, after simplifying. Okay, so you should not write directly. I'm writing because see here, there's no point in just sending. Okay, that you have to do it. You must do it. Okay, as taking LCM, cancellations on left side, right side, sending into the left side, and all shuffling it to get this form. Epsilon r plus 2 by epsilon r minus 1 equals to n alpha e by 3 r. Okay, this is said to be the Clausius-Moisseiff relation. Okay, so this is it. Okay, as far as your syllabus, see here the major part from the dielectric substances. The dielectric substances, what you have to do is to uh, initially the dielectric substances are not that much critical, but they're not that much typical. But what you have to do is to first find out some easiest things like definitions, and we have different types of polarizations, and then we have internal field, and then we have Clausius-Moisseiff relation. So this one, all you have to do is to practice it, then it will be easier. Okay, so let me check your syllabus what we have. Okay, so if you could do this, the internal field, Langen's orientational polarization, okay, that's fine. Then, okay, yeah, if you could cover this, that will be enough. Okay, so let's move on to some other topics in the same dialectics, but we'll understand more about the substances, or you can say that they are said to be the type of dialectic substances. Okay, just a moment. I would like to show always show something so that you can understand things better. Okay. So next thing is just as part of the discussion of the dialectic substances. Let's have a quick look at some of the whether they are important for the examination or not. Sometimes some professors may be giving, okay, for short questions or something like that, you have to have some idea about the dialectic breakdown. Okay. So the dialectic breakdown actually talks about the sudden change in the state of dielectric material, okay, subjected to a very high electric field. What happens? See, generally, when we are talking about the electric field, when the electric field has been applied to a dielectric substance, that's what I told you at one stage that see here, the more we are trying to send the electric field through a dielectric substance, the more it opposes. I said, okay, what happens if it is increased very much? If it is, let us say 150 volts has been increased, okay, has been straight away given to a dielectric substance, and 150 volts has been increased now to 200 volts and 300 volts, 400 volts, 500 volts. What happens if it is okay? If it is increased, that's where the dielectric breakdown takes place. Okay, so what happens is the dielectric breakdown is a sudden change in the state of dielectric material subjected to a very high field. Okay, so this is what when the high field has been applied to a dielectric substance, there is a sudden change. Okay, will take place. Under the influence, the electrons are lifted to the conduction band, causing a surge of current, and the ability of material to resist the current flow suffers a breakdown. Okay, so once again, the electrons are lifted into the conduction band. We have here the band. Okay, so we have valence band, we have conduction band. Okay, and being separated by a forbidden band. Okay, when the electric field has been applied to these dielectric substances, then as a result, what happens? Electrons, the electrons are lifted into the conduction band, causing a surge of current. Okay, it causes a surge of current, and the ability of the material to resist the current flow suffers a breakdown. So it does undergo a kind of a breakdown. Okay, that's one way of understanding the dielectric breakdown. Or sometimes in some textbooks they will be also be mentioning as when the dielectric material loses its resistance. If you prefer this type of way, you can go ahead. Okay, when the dielectric material loses its resistivity and permits a very large current to flow through it. Okay, that's a surge of current. So suppose if it doesn't strike to your mind, you can write this once again. When the dielectric material loses its resistivity and permits very large current to flow through it, then the phenomenon is called dielectric spectrum. Okay, and when this phenomenon is said to be here, the dielectric breakdown. Okay, there are many factors for the dielectric breakdown. Okay, that is one of them is said to be the intrinsic. One of them is intrinsic breakdown. Okay, intrinsic breakdown. Next one is thermal breakdown. The next one is discharge breakdown. Then electrochemical breakdown and defect breakdown. There are various types. Okay, defect breakdown. Okay, so very briefly, I will just tell you about the breakdown because if any case, in case of any questions coming from the dielectric breakdowns, you must be in a position to answer. Okay, the dielectric strength is defined as the breakdown voltage per unit thickness of the material. Okay, so what you have to understand is as a dielectric substance is being present, and the dielectric breakdown, what you have to understand is the voltage per unit thickness of the material. So, unit thickness of the material, when the applied electric field is large, some of the electrons in the valence band cross over the conduction band and the large forbidden energy gap, giving rise to a large conduction current. So, what happens is here, I'll draw the diagram and show it to you. Okay. Okay. We have actually, you have to understand, see, when you read this way, suppose if you say that we have here a conduction band, we have actually the valence band, there's the conduction band, there's forbidden band. Okay, this is what the you have to have some band theory concept. Okay, we have valence band, we have conduction band, in between is said to be the forbidden band. Okay, in between is said to be forbidden band. Okay, what he says is that suppose if the electrons present in the word valence band, they tries to enter into the conduction band, for instance, like this. Okay, with the application of electric field, with the application of electric field. Okay, so see, let us say that all the electrons are all being pushed towards the conduction band. Okay, they what happens here as a result? Okay, if the electrons are all going from the valence band on to the conduction band, okay, the more they are going towards the conduction band, then as a result there will be it will actually opens up. Okay, see here one electron, let us say, goes from the valence band onto the conduction band. Okay, it's not sufficient, and because this electric field we are forcing, we are further forcing, then what happens, another electron also goes. Okay, like this, second electron, third electron, all the electrons goes from the valence band onto the conduction band. Okay, if all the electrons make a transition from the valence band onto the conduction band, then as a result, what happens is here the forbidden band, there is some forbidden band is a restrictive band. Okay, that's a restrictive band, and it's like it's breaks. Okay, once it breaks, what happens? All the electrons will push it from the valence band onto the conduction band, and thereby the conductivity takes to the maximum. Okay, so completely all the electrons will be pushed towards that side, and thereby the conductivity takes place. Okay, and it no longer works like a dielectric. Okay, that's what. So it has got some threshold. Some only to some extent they can work like a dielectric substance, and further increase, and they go on, keep on increasing the dielectric substance leads to a complete. Okay, it won't work like a dielectric substance, but it starts working like a conductor. Okay, so that's what the thing is about the dielectric breakdown. Okay, so this is it. In the next class, what we'll have is, as far as your syllabus is concerned, we have actually many things to discuss, but here mm, we can go ahead with some other topics like very important ones. We have uh, the block theorem. Okay, the block theorem we have. Okay, and then we have chronic penny model. That's very difficult actually, to be honest. Band theory of solids, in which we have to discuss about the chronic penny model. Okay, block theorem. Okay, generally in any paper you see, in any examination, block theorem, uh, chronic penny model, generally they will be appearing in the examination. Okay, so in the next class we will try to derive those, okay, understand more about these. Okay, and I'll stop it here. Okay, thank you.
Thank you, sir.